Hey there! Do equations like this, and that, and these make you uncomfortable and lose hope in passing your pre-calc class? Well, that is not okay. And you made a great choice of clicking on this video because I made this guide just for you to save your grade. Now, I'm not saying this video is really easy to get on the first watch, but I promise if you spend some time to rewatch some parts and make sure that everything makes sense, you'll have an understanding of trig identities better than any of your classmates, and schoolwork will be a breeze. To make it clear, my goal in this guide is to answer two whys. First, why do trig identities work? And second, why do we need to know them? So let's get right into it. An identity is an equation in one or more variables that is true for all values of those variables. For example, if x is a real number, square root of x squared equals absolute value of x is an identity, since for any real x, this equation is true. In contrast, this quadratic is not an identity for real x, since it's only true for two values of x, certainly not all of them. As I said, identities can involve many variables, like these square of a sum identities, for example. Now, trig identities are identities that involve real numbers and the trigonometric functions, sine, cosine, tangent, so on. And your school probably gave you a long list like this of useful or important identities to memorize, all seemingly unrelated. I won't deny that memorizing some identities is needed for tests, but I want to show you where they come from, and also show you that they're all very related. In fact, just knowing three identities, namely the Pythagorean identity, the complementary angle identity, and the sine angle sum identity, you can derive algebraically every other identity on that list. Wait, what do I mean by derive algebraically? I mean that all we need to derive an identity is manipulating expressions with sine and cosine by adding, multiplying, and using the laws of algebra such as distributivity, equality, and so on. In contrast, deriving geometrically means to derive an identity by using the definitions of sine and cosine as triangle side ratios and other properties of geometric shapes like triangles and circles. Geometric arguments are usually less straightforward than algebraic arguments, so really we want to avoid them as much as possible. And this brings me to my main point. To derive every common trig identity, we only need to use a geometric argument on those three. The rest can be derived solely using algebra from them. So now I will show you these three geometric derivations, starting with the Pythagorean identity. We draw a right triangle labeling the sides A and B, the hypotenuse C, and an arbitrary acute angle theta. We recall the famous Pythagorean theorem, a squared plus b squared equals c squared, and use the definitions of sine and cosine to write two ratios. Remember that theta can be any angle. So when we square sine and cosine of theta and add them together, it is equal to adding the square of these two ratios. The numerator is a squared plus b squared, and the denominator is c squared, but those are equal by the Pythagorean theorem. So if c is not 0, which it never is, the ratio becomes 1. And so for any acute angle, theta, sine squared of theta plus cosine squared of theta equals 1. But how do we extend this rigorously to non-acute angles? That is actually a much more interesting topic than it seems, since there are many not agreed upon ways to extend the domain of sine and cosine, and hence many resulting definitions to use. But that kind of rigor is beyond what most students watching this video are looking for. So a satisfactory answer is that sine and cosine of non-acute angles still represent ratios of sides in right triangles, just the lengths can be negative. This is shown clearly with the unit circle. Since it involves angles in right triangles identical to acute angles, our proof applies. Okay, let's do the complementary angle identity. Again, draw a right triangle with sides labeled as usual and the two acute angles labeled alpha and beta. First, note that sine of alpha equals cosine of beta, simply by their definitions. Second, note that alpha plus beta is pi halves in radians, easily by the property of the sum of angles in a triangle. These kinds of angles are called complementary, by the way. Then beta equals pi halves minus alpha, and plugging that into cosine, we simply get the identity. We can again extend this argument to all angles with right triangles in the unit circle, and I think a great way to see this identity is graphically. Compare the graphs of sine and cosine. We transform cosine by reflecting it, getting the same graph, then translating pi half units to the right, getting the sine graph, and this is exactly what the identity tells us to do. Now for the big one, the sine angle sum identity. A lot would disagree, but I would argue that it is the most important trig identity out of all. We draw a triangle with vertices labeled ABC, and altitude dropped from B to H with length H, and the angle B split into two angles alpha and beta by the altitude. Let's first get the lengths of some other segments using the length H and trig functions of the angles alpha and beta. And now comes the trick. We can write the area of triangle ABC in two ways. First, using this formula with angle B, we get this expression. Second, we write it as a sum of the areas of triangles ABH and CBH, using the half base times height formula, like this. Now we can equate both of these expressions, remove the 1/2 from each side, and substitute for h and functions of alpha and beta to get this. Now removing h squared from both sides and isolating sine of alpha plus beta, we can simplify the right side a bit using definition of tangent, and we are done and get the identity. Again, an extension to non-acute angles follows with the manipulation of right triangles in the unit circle. If that seemed too condensed, you can check out old video of mine that takes the same proof a bit slower. Now that we've proved those three identities, the sky is the limit for the identities we can derive from them. Let's look at some important examples. First, parity identities. You probably heard that cosine is an even function and that sine is an odd function. We can now prove that completely algebraically using our three identities. Plug in x plus pi halves in the complementary angle identity to get sine of x plus pi halves equals cosine of minus x. Now, since we know the sine angle sum identity, we can expand the left side, and using the values of sine and cosine of pi halves and simplifying, we easily get that cosine of x equals cosine of minus x. And this proves that cosine is even. Now, getting to the parity of sine uses the parity of cosine. We see that sine of minus x equals cosine of pi halves plus x with the complementary angle one, and this equals cosine of negative pi halves plus x with the parity of cosine which we just established. Now, getting this to a form we want, we see this is equal to cosine of pi halves minus, in parentheses, x plus pi, which is simply the form of our complementary angle identity. So that is sine of x plus pi. Expanding this using the sine angle sum identity again, we get that sine of minus x equals minus sine of x as needed. Second, some more sum and difference identities. Say we want to find the sine angle difference formula. We'll just plug in negative y into the sum formula, expand this, and use the parity of sine and cosine which we just established. And doing just that, we get the same thing as the sine angle sum identity, but with a switch sign. Now let's try the cosine angle sum. Using our complementary angle identity, we see that cosine of x plus y equals sine of pi halves minus x plus y, and this equals sine of pi halves minus x in parentheses minus y, as shown. We can expand the sine part using the sine difference, and then use the complementary angle identity in between to get cosine of x cosine of y minus sine of x sine of y, which is the cosine angle sum identity. An exercise for you is to pause the video and find the cosine angle difference identity. As you can imagine, we can keep going with simple algebraic methods like this, proving more and more identities until we've rigorously established every identity on this list. Some are very straightforward, and others require a clever trick or two. So this is where I conclude the lecture on the first why trig identities work. Using geometry to derive three important identities, then using algebra to derive the rest, that is where trig identities come from. I'll leave you with a handful of derivation exercises before moving on to answer the second why we need trig identities. The clearest answer is that trig identities help simplify algebraic expressions that appear in several places. The questions you have in school probably require you to simplify things like these, and truth is certain expressions like these occur a lot in math and in applied math, and trig identities make working with them easier. I bet if you were an ancient mathematician that encountered a sine angle sum, or double, or half angle out in nature, you'd discover the identities I've been talking about pretty quickly to simplify your further work. I'll show you one concrete example to emphasize that simplifying some expressions is really important. Say you have a point in the plane with the given coordinates x, y, and you want to find the coordinates of that point after you rotate it by a given angle theta. It's a good problem, so pause the video if you want to think about it yourself. But now check this out. We can write the coordinates of our point in a peculiar way. Let's call the distance from the point to the origin r, and the angle the line from the point to the origin makes with the x-axis alpha. Dropping a certain perpendicular line on the x-axis, we can see a right triangle. Note here that cosine of alpha equals x over r and sine of alpha equals y over r, simply by their definition, and hence our coordinate xy equates to the coordinate r cosine of alpha, comma, r sine of alpha. And some of you may recognize this representation of xy with the name polar coordinates. Anyways, we can describe the rotated point in much the same way. Rotating xy by theta, our new point is the same distance r away from the origin, and the angle it now makes with the x-axis is alpha plus theta, since that's what a rotation by theta means. So the new point, which we'll call x prime comma y prime, equates to r cosine of alpha plus theta, comma r sine of alpha plus theta. Okay, but this expression doesn't help us at all if we can't express it in terms of x and y, since now we have two useless parameters, r and alpha. But remember, we know the values r cosine of alpha and r sine of alpha, and most importantly, we know the angle sum identities. So expanding this form of x prime y prime using the identities, we get this. And when we distribute r, note how we can substitute x and y for r cosine of alpha and r sine of alpha. And so we get that a point xy rotated by an angle theta has these coordinates, all in terms of x and theta and some trigonometric functions. How cool is that? We are able to describe a rotation in the plane, all thanks to our trig identities.